here is a direct proof example in which we are trying to show that the sum in the form of 1 squared plus 2 squared plus 3 squared up to n squared is equal to n cubed over 3 plus n squared over 2 plus n over 6. Can we prove this in a direct fashion? Okay, so basically what we are trying to show is the sigma or the sum notation from, let's say, k equal to 1 up to n k squared, which is exactly the representation of this total sum, or let's say s, is equal to this outcome. I'm going to use a simple trick. So let's write it this way. I'm going to write n plus 1 cubed equal to, as is well known, just two components raised to the power 3. So I'm going to write it n cubed plus 3 times the first term to the power 2, so n squared, plus 3 times the first component or first term to the power 1, and then finally the last one, which is 1 to the power 3, which is 1. So keep it as it is. Now the next one, what I can do is I can just write n, so let me put it this way. I can write n cubed effectively in the form of n minus 1 plus 1 cubed, because this whole thing is n. So, and then I can treat this as two terms, one term and another term, similar to what I did in the first one, to the power 3. So allow me to do that, because if I treat it that way, I can write it as n minus 1 cubed plus 3 times n minus 1 squared plus 3 times n minus 1 and finally plus 1. Okay, I can keep doing this, meaning that next term is n minus 1 cubed, which I can write it as, again, n minus 2 plus 1 cubed. So it's as if I have again two terms, one term, another one. So the same game I am playing, I can write it in the form of n minus 2 cubed, 3 times n minus 2 squared. So to just tidy up, let me just remove this portion. I'm going to write this as n minus 2 cubed plus 3 times n minus 2 squared plus 3 times n minus 2 plus 1 cubed, which is 1. Okay, so next one naturally is, of course, n minus 2. So I can keep writing this. Maybe this is the last one I'm going to try. Same idea. You can rewrite it in the form of n minus 3 plus 1. And again, treat them as two terms inside raising to the power 3. And when you do that, naturally, what you get is n minus 3 to the power 3 plus 3 times n minus 2, n minus 3 to the power 2, and plus 3 times n minus 2 and plus 1 cubed, which is 1. And you can keep doing this up to the point you get to, say, 3 to the power 3, that you can write it in the form of 2 plus 1 to the power 3. And then these are the two terms you raise into the power 2, which effectively become, just so that I'm writing them, let me remove it. Okay, so your terms are becoming now 2 to the power 3 plus 3 times 2 to the power, let me put it inside the parentheses as before, 2 plus 3 times 2 plus 1. And you can also do this for 2 to the power 3, which you can write as 1 plus 1 to the power 3. And these are the two terms again. So naturally, you can write it in the form of 1 cubed plus 3 times 1 squared plus 3 times 1 plus 1. So what is the game we are playing here? Okay, it is as simple as this game. So of course I can keep writing this, and the last one naturally will be 1 cubed equal to 1 cubed. But the game that I'm playing here is this simple trick here. So let me change the color so that you can see what I am doing. If I start adding up all these lines, then keep in mind that in all these terms I have left-hand side and right-hand side. So I'm going to highlight the equality so that you easily see what I mean. And I'm going to highlight these ellipses, ... Okay, so when I add all these lines, from the right hand side, n cubed cancel out n cubed from the left hand side. From the right hand side, n minus 1 cancel out n minus 1 cubed. Again, n minus 2 cubed cancel out n minus 2 cubed. N minus 3 cubed, the same thing. So these very first components or terms cancel out the only component on the left hand side of the equality. So this one is gone, and finally this one is gone. Okay, so what are we doing? What are we dealing with then? All right, so if you take a look at a very nice outcome, you can see that I have 3 times n squared, 3 times n minus 1 squared, 3 times n minus 2 squared, 3 times n minus 3 squared, 3 times 2 squared, and 3 times 1 squared. So there you go. The interesting, what you were looking for to sort of find, we are now forming it actually, because we are adding up all these lines, and one of the sums that is showing up is exactly what we want. So when we add up all these guys together, we end up exactly forming, let me highlight it on top, we end up exactly forming the sum that we want, this sum. So let's name it as S, okay? So I'm gonna name this as S. When I add up all these highlighted in green components or terms together. So on the, just as a recall, on the left-hand side of all these equalities, the only thing that is remaining is this component at the very beginning. So this one is the one that is just not canceled out. So when so let's say adding adding all terms, all lines, or all equalities, what I get is, on the left hand side, I only get n plus 1 to the power 3. On the right hand side, I get 1 to the power 3. So maybe I change the color so that it goes back to what you guys are comfortable. So it goes to equal to 1 to the power 3 plus 3 times s. So s is the sum of interest that we want to compute, plus 3 times. Interesting. Another interesting summation that is showing up is, maybe I use a different color that you can see it, is this sum. 3 times n minus 1, and sorry, I need to make this n minus 3. Okay, so there you go. So effectively what is showing up is the famous sum, which is 3 times 1 plus 2 plus 3 plus ellipsis up to n. And finally, what else I have? Well, you can see that I have, I am adding up n times 1 together, because effectively if I highlight it also so that it's observable, maybe I use a different color. Okay, I am adding up 1 n times together as I'm adding these last terms. So it's going to be n times 1, obviously. Okay, so in summary, what I found is, if I expand on this, or if I can keep it for now, what I found is n plus 1 q is equal to 1 plus 3 times s plus 3 times, well, this one is pretty well known. It's n times n plus 1 divided by 2. So n plus 1, n plus 1 divided by 2, and plus n. So almost there. Okay, in the sense that if I go back to the black color, okay, so what is the benefit of this? Well, if you just take a look at what we got, we have, so if I just compute what I get for s, I get, so let me just make sure that I'm, okay, so what I get is ns is equal to Okay, s is equal to, I get n plus 1 to the power 3, and then maybe I can just raise it to the power 3. I was trying to be smart about it, do something quick, but let's just do it systematic and brute force. So n plus 1 to the power 3 is n cubed plus 3n squared plus 3n plus 1, and moving all the other components to the other side. And of course I have 1 over 3 that I need to multiply everything, because, or I can just keep the 3s over there to keep it neat. So I'm going to keep 3s here, and I'm going to move everything, meaning these guys, to the other side, to the left side. So I get minus 1, which is the impact of this, and then I get minus n, which is the impact of this guy, and again I get minus 3 times n plus 1 divided by 2, which is the impact of this term. Okay, so let's just simplify. And what I get is, I get just n cubed, and I get 3n squared, and then minus 3n squared over 2, so it becomes just 3n squared over 2, and I get 3n minus n, 2n, and then I have minus 3n over 2, so it becomes effectively just plus n over 2. Alright, so that is the outcome for 3s. So therefore, naturally, as a result, what I get is s, the sum of interest, is just obviously n cubed over 3, this component, divided by 3, and then next one is n squared over 2, because this 3 cancels out, and then we have finally n divided by 2 and then divide by 3 as well, so divide by 6. This is exactly what we wanted to prove, and that concludes and completes the proof for this direct proof example. Of course, the best method to use for, generally speaking, proving these kind of problem is mathematical induction, but this is just a showcase of that it can be also proven in a direct fashion using other than mathematical induction method. I hope that this example is helpful.